Hello again, George Notchik here. This is the second in a series of videos that is discussing the movement of the Earth and the Moon within the heliocentric model of our solar system. There is an interplay of motions that the Earth and the Moon have with respect to the Sun that results in some curious observations, one of which I've been asked about several times since releasing the first video. The question is, why do we only see one side or face of the Moon if the Moon also rotates about its own axis? The reason is called tidal lock. Tidal locking occurs when there is no net transfer of angular momentum between the Moon and the Earth. This results in the Moon rotating about its axis once for the same amount of time that it takes for the Moon to make one complete trip around the Earth. Millions of years ago, the Moon spun at a much faster rate than it does today. The gravitational influence of the Moon pulling on the Earth and the Earth pulling on the Moon acted to slow the Moon's rotation by transferring some of its angular momentum in the process. This influence slowed the rotational period of the Moon to match that of its orbit today, which is around 27 1/3 days. And it is now locked into this period with no net transfer of angular momentum between the Earth and the Moon. Before I describe the mechanism that causes tidal locking, I'll first answer the question as to why we see only one side or face of the Moon as the Moon orbits the Earth. I have here a diagram that shows the Earth and the Moon. We have the Earth at the center and the Moon is orbiting the Earth. And I'm showing the Moon at five different positions as it makes one complete revolution around the Earth. Now keep in mind, this is very similar to what I just talked about in the first video where we talked about ellipses, the heliocentric model, and Kepler's laws. Kepler's laws are valid not only for movements of the planets about the Sun, but also about the moons orbiting about their individual planets. Each one of these systems are what we call a central force system. In a central force system, you have a more massive central primary body and less massive satellites or orbiting moons about the primary central body. And the trajectory or the path that the orbiting bodies have around the central body, they trace out ellipses. And the elliptical path is such that the central body, the more massive one, is situated at one of the foci of the ellipse. Now, a property that I discussed then about that describes the what the ellipse looks like is called its eccentricity. In the case of the Moon, the eccentricity of its orbit is 0.055. And the eccentricities can go between 0 and 1. When the eccentricity is 0, the ellipse becomes a perfect circle. And when the eccentricity is 1, the ellipse collapses into what's called a degenerate ellipse and just becomes a straight line. So, in general, an elliptical path will look something like this. We have a major axis and we have a minor axis. And the relationship between these axes is related through the eccentricity. Now, in the case of the Moon, we have a near perfect circle because the eccentricity is very close to 0. Now, let's look at what happens as the Moon rotates in its or orbits about the Earth in its near circular path. I'll start the Moon off here, and the red will show the side and the face of the Moon that is always facing the Earth. And with respect to an observer on the Earth, we're going to trace out point A, which is on the left edge of the face. So in position 1, our point of interest is on the left edge here. And what these lines show are the axis, the orientation of the axis. As the moon rotates about the axis remains fixed, and we're going to use this line to as a point of reference so we can keep track of where this point A is as the moon orbits about the Earth. So in each case, the axis will remain fixed, oriented to space, and I'm showing that here. We have the same axis orientation as we do in each one of these positions, and this is the moon. And what I'm putting here are the points A for each one of these positions. And so we have the axis of the moon that's oriented, fixed in space, and this is the perimeter of the moon. So let's start at the first position. Point A is a little bit to the left by about 30 degrees from the orientation of the axis. So this actually should probably be a little more like right here. So that's point A at position 1. Now, when the moon moves into position 2, remember the moon rotates about the in its orbit, or not rotate, but orbits about the Earth in a counterclockwise direction when you're looking down from the North Pole. The North Pole axis of the Earth, the moon rotates in a counterclockwise direction. So at position 2 here now, the left edge of the face is here a bit to the right side of the axis orientation. And when we come down to position 3, we're still looking at the same face and looking from the Earth. This is the left edge, point A. Point A now is almost 90 degrees from the axis, and that's at this point. Now at position 4, again, this is the face that we always see from the Earth, and looking from the Earth, the left edge, point A now is a bit to the right side of the orientation. So this is point 4 now for A. And then when we go to 5, we're looking, the left edge of the face of the moon is over here, which is looking, close to about, probably about 70 degrees to the left of the axis. So this actually should be probably a little bit over here. So what happened? Let's look and see what's happened now. We're always looking at the same face as the moon goes around the Earth, but look what happens to this fixed point on the surface of the moon. It actually makes one complete revolution with respect to the axis. And you can see that. I'll take this baseball and just watch the threads. In this case, this is the face that's always going to be facing the Earth. Now watch what, if we have our axis of the moon right here, little dot, watch what happens with this orientation line as I go around the Earth. So we're coming down to this. We're still facing the same face. And then we come here. So the moon makes one complete revolution as it goes, making one complete orbit about the Earth here. So what happens is, the reason why we always see the same face of the moon is the fact that the moon is rotating once around its axis as it makes one complete trip around the Earth. And so the moon does rotate once around its axis, and because of that, we always see the same face of the moon. I will now discuss the mechanism that causes tidal locking. I have here a diagram depicting the Earth and the moon, not to scale of course, and I've drawn a radial line which we call the principal axis between the Earth and the moon. The principal axis goes between the center of mass of the Earth and the moon, and when we look down at the Earth from the north axis, the North Pole axis, the Earth rotates in a counterclockwise direction. So does the moon, and the moon also orbits about the Earth in a counterclockwise direction. Now we're going to assume we're looking back in time to when the moon was not tidally locked to the Earth. Millions of years ago, the moon spun around its axis at a much faster rate than it does today. The gravitational influence of the moon pulling on the Earth and the Earth pulling on the moon acts to slow the moon's rotation by transferring some of the angular momentum in the process. This influence slowed the rotational period of the moon to match that of its orbit, which is about 27 1/3 days today. And when that happens, the moon becomes locked into this period with no net transfer of angular momentum between the Earth and the moon. Once the moon becomes tidally locked to the Earth, then its rotational period matches its orbital period, and we end up only seeing one side or one face of the moon as it makes one complete revolution or one complete orbit about the Earth. Now, the gravitational pull of the primary body, which is the Earth, on the secondary body, the moon, creates a tidal bulge on the moon. This tidal bulge causes a gradual recession of the moon away from the Earth, as well as locking itself tidally to the Earth. Now, the gravity of the Earth produces a tidal force that squishes the moon. So what happens here, the gravitational equilibrium of the moon gets distorted because of the gravitational pull of the Earth. And what we end up with is the moon getting slightly elongated. Let's just show it this way. Becomes slightly elongated, and this is what we call the tidal bulge. That is, the surface of the moon is bulged out from its gravitational equilibrium state. Now, when this happens, keep in mind that it is the material mass of the moon itself that is getting distorted. The bulk of the moon is getting elongated, and now when the moon isn't tidally locked, this elongation is going to be rotating, and let's just say it is moved off now like this, and then what will happen is, if we say this is the principal axis, now this portion of the moon will relax back and it will get bulged out again this way. So what happens as the moon is rotating, we have a shifting. This equilibrium shape travels over the surface of the moon as it's rotating, with the high bulge, this high bulge being closest to the Earth, or would be located symmetrically about the principal axis, because the gravitational field is strongest here. So as this rotates, you can imagine that this bulge travels around the moon, that as the moon is rotating, this bulge remains here, but we're looking at a different part of the surface of the moon as it's rotating. So the high bulge is constantly shifting the shape of the moon. The material of the mass of the moon exerts a resistance to this periodic reshaping caused by the tidal force, which produces a time lag, if you will, both in creating the tidal bulge and returning back to its equilibrium gravitational shape. The equilibrium gravitational shape is a sphere, and as the moon is rotating, this bulge is moving off, so this portion of the bulge shifts back, tries to get back to the equilibrium state when a new part is bulging out of the moon as it's rotating around. Now, what happens here is by the time these bulges form as the moon is rotating, what happens here is, let's see here, is if we look, this bulge now tends to move off the principal axis. It doesn't react instantaneously, so it's still bulged as it's rotating around, and then as it gets more and more off center from this principal axis, then it starts receding back into the equilibrium state, and then a new portion, of course, bulges out here. Now what that does is it creates a situation where the bulges are displaced from the major axis. So let's just look at an instant in time when this has rotated a bit, and what we end up with, say this is exaggeration, is the bulge that we had here is now moved over. The mass does not respond instantaneously, so it takes a while for this to recede back to the equilibrium state. But when that happens, as it's moving off, we still have a gravitational pull. The gravitational pull is in this direction, and that creates a torque. If you look at the radial distance there, it's no longer in line, so it tends to it applies a torque that tends to rotate that elongation back in line with the principal axis. And we also have the bulge out here, and the gravitational force here is pulling in that direction, which is tending to counteract the torque. It's a torque in the opposite direction. But what's going on here is that this mass is closer to the Earth by 1 moon diameter than this, So this torque, call it T1, is a little bit greater than T2. So the net torque overall is to try to rotate the elongation of the moon back in line with the principal axis that joins the center of the Earth and the moon. So over time, this action causes the moon to eventually orient itself so that the elongation is right in line with the principal axis as it orbits the Earth. And at this point, when that happens, we call it tidally locked. There's no more exchange of angular momentum because any vector from the Earth, gravitational vector, if we look on either side, we have a gravitational force pulling that way, one pulling that way. If we have distance vectors that go out, this one's creating a torque in that direction, this one's creating a torque equal and opposite in that direction. There's no net rotation. There's no net change in angular momentum. And that is what we have when the moon becomes tidally locked to the Earth. I'm going to summarize the tidal locking mechanism. Things got a little bit messy, so I cleaned it up a bit and just very quickly go through it. I'm going to summarize the tidal locking mechanism. Things got a bit messy there at the end. I cleaned it up, so I'll just go through it real quick here to illustrate the principle. Now remember that before the moon gets tidally locked, it is spinning about its axis much faster than it currently is. It's spinning in the counterclockwise direction, and at, say, this point in its rotation, what happens is we end up getting the moon squishes a little bit because of the Earth's gravitational pull is elongating the moon, and then as it's rotating, the elongation moves off the axis of the primary axis here. So what we end up with is getting something like this. Where the tidal bulge is no longer in line, the axis of the elongation of the moon is no longer in line with the principal axis. So what happens is we end up getting a torque and a twisting action. A torque is when you have a radial line, say, to a point of mass here out in the bulge, and that piece of mass here, unit mass, is attracted towards the center of the Earth by the Earth's gravitational pull. So we end up with a force vector that's pulling in this direction. And you can see from the diagram that we end up getting a torque. A torque is a twisting action that causes a rotation about the center of rotation for the body, in this case the moon. So what tends to happen here, as you can imagine, is as this force is pulling on this bulged out mass, it's tending to rotate it towards the center mass, towards the principal axis of the Earth-Moon system. And then after time, after enough of these rotations over a length of time, what happens is this elongation of the moon orients itself so that there is no net torque or exchange of angular momentum. So over time, what will happen is the elongation of the moon will orient itself so the axis of the elongation is in line with the principal axis between the Earth and the moon. And when that happens, you can see the gravitational force lines don't create any torque at this point. So the system stops. There's no more exchange of angular momentum. If you look at a point here and a symmetrically located point there, we end up with, say, a radial line there, a radial line there, and then a gravitational force is pulling that way and one pulling that way. So this one's tending to create a torque in that direction. This is creating a torque in that direction. They balance out. So once the elongation of the moon orients itself with the Earth, there's no more torques, net torques being developed, and so the moon now becomes in lockstep, or what we say is tidally locked to the Earth. Tidal locking also has other consequences. The moon is moving away from the Earth at a very slow rate of about 4 centimeters per year, more exactly 3.78 centimeters per year. That's about the same speed at which our fingernails grow. The movement of the moon away from the Earth is due to the action of the Earth's land and sea tides caused by the moon. The moon is kept in orbit by the gravitational force that our planet Earth exerts on it. However, the moon also exerts a gravitational force on the Earth and causes the Earth's oceans to move and to form tidal bulges, just like we saw on the moon. This is responsible for the tides of the Earth, which rise and fall the sea levels each day. The tides arise because the gravitational force of the moon is not uniform across the Earth. The nearest side of the Earth is attracted more strongly to the moon than the furthest side. Due to the rotation of the Earth, the tidal bulge actually sits a little bit ahead of the moon's center of mass. Let's consider this diagram. We have the Earth. The Earth is rotating with an angular momentum omega e in a counterclockwise direction, seen looking down from the North Pole at the Earth. The moon is orbiting about the Earth, also in a counterclockwise direction. As before, I've drawn a principal axis between the center of mass of the Earth and the center of mass of the moon. Now, just like on the moon that had tidal bulges, we get tidal bulges on the Earth due to the moon's gravitational pull. So you can imagine that the Earth gets a little bit elongated, just like the moon did. And we have two bulges, one in the front and one in the back, as the Earth gets squished. Now, because the Earth is also rotating on its axis, this tidal bulge, rather than being symmetrically located about the principal axis, actually moves ahead a little bit of that axis because of frictional forces between the ocean waters and the landmass beneath the ocean. So this bulge actually, rather than being symmetrically located, tends to shift like this. It's a little bit ahead. Say this is the line of symmetry for that bulge. it actually moves a little bit ahead in the direction of rotation from the line that goes between the center of the Earth and the center of the ocean. And this is due to friction between the ocean waters and the land surface beneath the oceans. This drives the bulge forward, keeping it ahead of the moon slightly. The tidal bulge that we get here feeds a small amount of energy to the moon by pulling on the moon, pulling it in this direction, that creates a forward acceleration. And that forward acceleration, that slight forward acceleration, moves the moon into a higher orbit until it is balanced by a reduction in its kinetic energy of motion. I'll show how that works here. Now imagine we have this leading tidal bulge because of the frictional forces between the ocean and the mass of the Earth, the land mass of the Earth, because of the rotation of the Earth. Now, if we look at what happens here is as the moon is orbiting, it's going to be trying to maintain a constant radial direction. So the moon's going to try to move in this path without any, if we didn't have any tidal bulge, the moon would be moving a uniform distance from the center of the Earth. But because of this tidal bulge, we now have a vector force that's not directly in line with the center of masses. The center of mass of the moon now experiences a vector to the bulk of the tide here. So what happens? Well, if we look at this and decompose it into components, one component directly in line with the centers of masses, which is in the principal axis direction. So we can imagine we have this force vector going developed by the bulk of the tidal force, which is just a little bit ahead, moved a little bit ahead. And then we also have a component this way. So if we look at our vectors, this is our principal axis vector. And then this is the actual force vector to the bulk of the tidal force here. And then we'll have a component in that direction. So we can decompose this net force to the bulk into two components. One directed radially between the centers of mass, which keeps the moon moving in this circular path, a uniform distance from the Earth. And then we have a slight little vector in this direction. These two vectors here would be parallel. So we can see what's happening is because this bulge, tidal bulge, is a little bit ahead of the center of mass of the moon, we get a component that tends to move the moon out away from the uniform orbital path that it would take without this bulge. So what this tends to do is accelerate the moon out of its orbit. And it will move out of its orbit until it reaches a new equilibrium. So rather than taking this path, this constant distance away from the Earth, the moon is going to move further into a new orbit until the energy gain, which was fed by the tidal bulge, is balanced by a reduction in the moon's kinetic energy and a gain in its potential energy. It gains potential energy because it is moving further away from the Earth. So the moon now will move into its new orbit, which is a little further away from the Earth. If we call the original orbital distance before the moon gained some energy from the tidal bulge, we'll call this distance from the Earth center of mass to the moon center of mass, R1. This is the original orbital radius. And we'll call the new orbital radius R2. And originally, the moon had an orbital velocity of, we'll call it VT1, and the new orbital velocity we'll call VT2. By Kepler's laws, we know that a larger orbital radius is accompanied by a lower orbital velocity. That is, we could say that the new orbital velocity is equal to the old orbital velocity times the square root of the ratio of the orbital radiuses, or radii. Now, we know that the original orbital radius, R1, is less than the new radius, R2. So if we ratio them, we can write R1 to R2 is less than 1. If the ratio of R1 to R2 is less than 1, then the square root will also be less than 1. Now, if we multiply each side by the original orbital velocity, and we see that this expression is nothing more than the new orbital velocity, we see that the new orbital velocity is less than the old orbital velocities. I will drive this equation at the end using Kepler's laws. So we see that the acceleration provided by the Earth's tides actually slows the moon down. Eons ago, the Earth days were shorter, but with the moon's braking effect operating on the Earth days have slowed down to 24 hours that we experience today. And the Earth's rotation period, which we call our day, will also continue to slow down into the future because of the energy exchange due to the tidal effects. We know this is true because we can look at the growth bands of coral in the oceans. The number of days that occurred per year in the past periods can be calculated from these coral bands, and we find that we can see that the days are getting longer by about 15.2 seconds every million years, which is an hour every 257 million years. 237 million years. Every 237 million years, the Earth will slow down by 1 hour in its rotation about its axis, so the days will get longer. comment. I heard on the internet some people talking about gravity and the heliocentric model. The claim is that if gravity existed, we would expect that the moon's orbit would decay and eventually the moon would crash into the Earth, so there can't be any gravity. Well, that's wrong. Out in space, there isn't any atmosphere out there to cause any drag on the moon, to cause its orbit to decay. And besides, we saw that the effect of tidal bulge is to actually transfer some energy to the moon to cause it to move away from the Earth, to cause its orbit to expand rather than decay. So this argument that there can't be any gravity because otherwise the Earth or the moon would crash into the Earth is just nonsense. It doesn't. Well, we've come to the end of the journey on this particular video. I want to make a few comments before I go ahead and do the derivation of orbital mechanics using Kepler's third law to get the equation that I used earlier relating orbital velocity to orbital period and the orbital radius. My plans in going forward to do a few more videos with the upcoming total solar eclipse. The next video I do will be addressing the total solar eclipse. We'll be looking at the umbra, the penumbra, and how the eclipse does indeed work on a spinning spherical Earth in the heliocentric model. We'll look at the timing of the shadow and how it is possible that the shadow will go west to east on the day of the eclipse, in spite of the fact that the Earth also turns west to east. The numbers all work out. I'm also looking at doing a segment on space communications to show how it is possible for us to communicate with the Mars rover on planet Mars from here on Earth, that indeed there is enough signal strength to get to the Mars rover and back, and also be looking at doing the attenuation and signal strength that we'd get back from sending an electromagnetic signal to the moon and doing moon bounce, which ham radio operators do quite frequently. That this is all possible, that some of the claims out on the internet that it isn't possible to get enough signal back from the moon or Mars is just total nonsense. It's very possible with modern technology that we have, and I'll go through that to show how it is indeed possible given current receiver sensitivities, antenna gains, and transmitter powers, and looking at the attenuation going through space and through the Earth's atmosphere and how it all works out. And I also would be looking at doing a segment on reflected sunlight from the full moon to show that the moonlight we do receive from a full moon is easily predicted and comes well within the range of what we would calculate given the reflectivity of the moon, its albedo, and attenuation through the atmosphere and dispersion. Know that the numbers come in very close, which shows that it isn't necessary for the sun or the moon to be self-illuminating to get the moonlight here on Earth. It is indeed reflected sunlight. And then another segment I'm looking at doing is investigating Maxwell's equations. Show you what Maxwell's equations and the side equations, side conditions for Maxwell's equations, what that looks like, and solve a few simple boundary condition problems. Show how Maxwell's equations predicts electromagnetic waves and also correctly predicts the speed with which these waves will propagate through free space, which is the speed of light. and do a few other simple problems and explain the equations to you to show how Maxwell's equations are used in solving boundary condition problems and making predictions in electronics, such as Kirchhoff's voltage laws and Ampere's circuit laws. All of that is contained within Maxwell's equations. So if there are any other topics that any of you out there might like to have addressed, just leave them, your requests, in the comment section. I'll look at it, and if the requests seem reasonable within my capabilities, I'll go ahead and try to produce a video to address your questions. So now I'm going to go ahead and do the derivation on the orbital mechanics using Kepler's third law. Now, as a final exercise, I'm going to use Kepler's third law, the general form that I derived in the first video, to arrive at a relationship between an orbital period, the orbital radius, and the orbital velocity of an object like the moon orbiting about the Earth, and finding a relationship what happens when the orbital radius changes so that the moon, for example, jumps into a new orbit. What we have here are two orbits. In the center, we have the Earth, and we have the moon orbiting about the Earth. The initial orbit has an orbital radius of r1. It has a period of tp1, and the orbital velocity, which is the tangential velocity, linear tangential velocity, is vt1. And the moon is orbiting about the Earth with radial velocity or angular velocity omega 1. Now, if we impart some energy, put some energy into the moon to cause it to jump into a new orbit, that is, we're going to be increasing its potential energy so it moves out further away from the Earth. It will then establish a new orbital radius of r2 with a new period we'll call tp2, and a new orbital velocity vt2, and a new angular velocity omega 2. So we want to find a relationship between these parameters, and we'll do that using Kepler's third law. So we first look at what we know. We have the initial orbit with r1 orbital period tp1, and then we're going to jump into a new orbit with radius r2. So these are the three parameters that we're going to know. Now we want to find what is the relationship between the orbital velocities from the initial orbit to the new orbit, vt1 and vt2, and what is the new orbital period, tp2. And also we can put in here omega 2 and omega 1. So we're going to start off with Kepler's third law that I derived in general form in the first video. So Kepler's third law tells us that the orbital period squared is equal to a constant times the orbital radius cubed. And this constant is 4 pi squared over the gravitational constant, many call big G, times the mass of the Earth, or plus the mass of the moon. So for this problem, the mass of the Earth and the mass of the moon don't change. Big G is a constant, 4 and pi squared are constants. So K is a constant in this problem. It never changes. Using this now, we can write out a relationship that the period of orbit 1 squared is equal to the constant times the orbital radius cubed. And in the second orbit, we have the same relationship, that the orbital period squared is equal to the same constant times the orbital radius cubed. Now I can ratio these two equations to get a relationship. We can just divide the two equations, and if we do, the constants cancel, and we get that the orbital period ratios squared is equal to the ratio of the orbital radii cubed. So this is our first equation here. Now we can get a relationship between angular velocity and the tangential velocity. The tangential velocity, or orbital velocity of the moon in its second orbit, is equal to the angular velocity times the radius of the orbit. And the same thing holds for the initial orbit, where the orbital velocity is equal to the angular velocity times the radius of the orbit. Again, we can ratio these two equations. And we get that Vt2 over Vt1 is equal to omega 2 R2 over R1 and omega 1. Now, we can get a relationship between the omega 1s and omega 2s in terms of the periods, the orbital periods, because the angular velocity is nothing more than the circumference of the circle in radians, which is 2 pi radians, and we divide that by the orbital period. That is the angular velocity. And likewise, we can do this for omega 1. Now we can ratio these two equations, so we get omega 2 over omega 1 that we have here. So we get omega 2 over omega 1 is equal to 2 pi over the period divided by 2 pi, and I can bring the TP1 up on to the numerator. The 2 pi's cancel, and so the ratio of the angular velocities is equal to the inverse of the orbital periods. Now what we're going to do is substitute now in for omega 2 over omega 1 in this equation. So I'm putting this in. So instead of omega 2 over omega 1, I'm going to write the orbital period 1 over the orbital period 2, the ratio of the orbital periods, and then R2, R1. Now, we also know that we have a relationship between the periods and the radius here, and we have a relationship here. Now what we're going to do is go ahead and eliminate the periods in this equation. So what I'm going to do is rewrite this equation. I'm going to isolate TP1 over TP2. To do so, we just cross multiply. We multiply both sides by R1 over R2, so it cancels there. So in here we have R1 over R2, VT2 over VT1. Now we can take this ratio and substitute it into this equation. And the way we'll do that, before we do it, we'll square both sides of the equation, since TP1 over TP2 is squared in the equation. So I'm going to take this and square it, both sides. Now let's put it into this equation. So TP1 over TP2 squared is this value, and that is equal to R1 over R2 cubed. We're now going to focus on this part of the equation. I'm going to isolate the tangential velocities, or the orbital velocities. So I will write this as R1 over R2 squared, VT2 over VT1 squared is equal to R1 over R2 cubed. We'll multiply both sides of the equation through by R2 over R1 squared, or cross multiplying to get rid of the R1, R2 on this side. So I'll go up here, so we can now write this as VT2 over VT1 squared is equal to R1 over R2. The exponents, we got a power of 2 here that can subtract from this power of 2, so the 3 becomes a 1. So this is equal to R1 over R2 to the first power. Now let's solve for VT2 in terms of the rest of the parameters here. I'll put this in green. This will be our final result. So this is VT2 is going to be equal to VT1 times the square root of R1 over R2. If we take the square root of both sides, this goes out, we get the square root here, and then if I bring VT1 over, we get VT2 is equal to VT1 times the square root of R1 over R2. This is the final result. What this tells us now is that if we have an initial orbital velocity, VT1, and we jump up to a expanded orbit where R2 is greater than R1, we can see if R2 is greater than R1, then this number in the square root will be less than 1. So the orbital velocity, the new orbital velocity, will be less than the original orbital velocity, because this here is less than 1. So VT2 will be less than VT1 by that particular ratio. So that's where the equation came from that I had used in an earlier segment of this video.